about solar cells. Wonderful. Yeah, so hi everyone, I'm Christine, and just a slight correction in the program. It says high mobility, high work function transparent conducting oxides, but unfortunately today I only can talk about high mobility transparent conducting oxides. So what exactly is a transparent conducting oxide and why do we care about it? So as you may recall from a previous presentation, a solar cell consists of primarily three parts right here: the absorber layer, which was previously discussed, and two contacts, back contact and front contact. The TCO, transparent conducting oxide, operates as the front contact, and it has three purposes. The first is as a window for light to pass through to the absorber layer in the solar cell. The second one is obviously as a front contact. It has to be a good electrode for carrier transport out of the solar cell. And the third is as an anti-reflective coating. So, what makes a good TCO? Well, there are a few desirable characteristics that we want to have. The first is that we want to have a wide bandgap TCO. Basically, just to summarize from something that's brought from the previous presentation, the bandgap is the amount of energy that has to be absorbed by a material before it can consider it conductive. So, if you have a wide bandgap, that means that a lot of the possible energies, if they're smaller than the bandgap, will pass through the material unabsorbed. Since we want our TCO to operate as a window and not as an absorber, this is ideal. This in allowing us to absorb the maximum portion of all available incident light from the sun. The second one is that we want our TCO to be what is known as degenerately doped. This is a way in which we can kind of trick the material into behaving in a way that it doesn't naturally behave. How we do it is we insert high amounts of a specific type of impurity that introduces free charge carriers into the material. If we basically cram as many carriers as we can into this material, what will happen is that our TCO, which is normally an insulator, will begin to behave instead like a metal and conduct electricity. The third obvious characteristic that we want of a transparent conducting oxide is that we want it to be transparent. This is for obvious reasons, namely that so light can pass through. So you may ask, what about mobility? You didn't say anything about that. But actually, mobility is highly tied to the second most important part of the TCO. It's conductivity. Conductivity is primarily dependent on three things: electric charge, which is a constant, the number of carriers that you have in the material, carrier concentration, and this how fast these charges can react to an electric field through mobility. If you want to increase the conductivity of your material, the obvious thing to do would be just to stuff more carriers into the material through doping. However, this can have unintended consequences for your material in other aspects, particularly in terms of its optical properties. I have here a graph that depicts three different materials with varying carrier densities. This is a graph of the absorption of various wavelengths of light from various materials. You may notice that towards the end of this graph, there's a portion where the absorption curve begins to flatten out. This is known as the free charge carrier absorption region, where basically absorption is not occurring by the material itself, but by basically the free charge carriers in the material. As you can see, as your carrier density increases, your absorption increases. This is bad if you want a transparent material, which depends on light transmission. Since we can't increase the conductivity by increasing the carrier density then, in order to have a highly conductive TCO, we should increase mobility. So, I will now start to get into the finer details of my research, and I'll start off with how I decided to deposit my films. The method that I chose is called pulse laser deposition, or PLD. And in this method, basically what you have from the student here is laser pulses of a set energy and frequency enter a chamber, strike a target, blow up the target, send a plume of material towards your substrate, and deposits on the substrate. For me, the target that I chose was a 95% indium oxide, 5% molybdenum oxide target. Just the material that I chose to focus on is molybdenum doped indium oxide. So another important aspect in the development of a film is how you can characterize it, how you can see if your material is good or not. One such way to characterize the material is through the Hall effect. I won't go into detail about what the Hall effect is, but what it can give us is two very important parameters: carrier concentration and mobility. These two factors, if you might remember from earlier, are very important in getting an idea of how conductive our material is. So here I have some of the results from my Hall effect measurements for three different films: indium tin oxide, or ITO, grown at room temperature, indium tin oxide grown at 500 degrees Celsius, and my IMO sample grown using PLD. The reason why I have the ITO data up here is to provide some sort of standard, as ITO is currently the most commonly used TCO in industry today. As you can see, basically this graph shows the best results that I was able to achieve for each of these three respective films. And you might notice that my sample is performing dismally. This is problematic. The problems did not stop there, as even for the mobility, my IMO sample was not able to beat out the best ITO sample that I was able to accomplish. Recall that I would like a very high carrier concentration, fairly high mobility for a good TCO in general, not even looking at ITO. But yet, my IMO film clearly was not able to achieve either one of those. This was particularly worrisome. So, moving on briefly to another aspect before just of my film, also important for our films to be transparent. So I had to examine the optical properties of my film. I did this by using UV-Vis spectrometry, which is a technique that allows one to measure the amount of light reflected or transmitted through a material. Some simple manipulation allows me to look at the absorbance of each film. In the graph here at right, I've boxed in a green region that shows the approximate visible light region for the observance graph, which corresponds to the most highly intense portion of the solar spectrum. You may notice here that we have the highest absorption of the visible light region with my IMO sample. This again is also worrisome because basically I want that light to be transmitted through to the absorber layer. In fact, we had a lot of problems trying to achieve a transparent IMO film grown by PLD. Here I've got a picture of two of the most common problems that we encountered. A depicts a sort of light-gray opaque metallic layer. In fact, this is due to the deposition of a metal instead of an oxide on our film. And this was the result of the laser simply being too powerful and chemically reducing our material before it was deposited. We attempted to correct for this by growing our films in an oxygen-rich atmosphere. The second one shows over-oxidation of the film, resulting in this dark brown-gray color. This was due to overexposure to oxygen, ironically the reverse of the previous problem. We attempted to correct for this by carefully controlling when we exposed the film to oxygen. So, what was the culprit behind these issues with transparency and also with the conductivity? What made my results so dismal? The answer could be found when we looked at basically the chemical state of the molybdenum inside of our film. And we did this by using XPS, which is X-ray photoelectron spectrometry. Basically, I have a small figure here that just shows the oxidation states of molybdenum inside of our film at different growth temperatures. As you can see, as we reach higher and higher temperatures, the prominent MO6 plus peak begins to broaden out as more oxidation states become more prominent. This is problematic since these other oxidation states give us opaque versions of molybdenum oxide, which we don't want. So, obviously I have this terrible film. So the solution was to try again using a new deposition method. And this one was actually a combination of two deposition methods, PLD and evaporation, which I have a picture of the diffusion cell that I used, or actually a schematic that is used in evaporation. Evaporation is a simple technique in which you take a material, you heat it up to extremely high temperatures until it basically evaporates and then deposits onto your substrate. We were hoping that by using this fusion technique instead of pure PLD, we would be able to more closely control the chemical state of the molybdenum oxide in our film. So the question is, were we successful? I have the same figures here from earlier, plus the Hall effect results from the sample of IMO that we were able to deposit using PLD and evaporation on the right. As you can see, in both cases, our new sample of IMO grown by PLD and evaporation was vastly able to outstrip anything else from the competition, especially in terms of the mobility, which we were looking for because we wanted to grow a high mobility film. Unfortunately, I wasn't able to also confirm the optical properties, but I did attempt to do so by visual inspection. So this picture here, unfortunately it's a little dark, but as you can see, it's pretty much transparent, which is good. We have TCO. So in conclusion, I set out to develop a high mobility, transparent, conducting IMO film. And I was able to do so eventually by using a combination of pulse laser deposition and evaporation. This new IMO film was able to accomplish incredibly high mobilities, and in fact, it has superior mobility to all of the other oxides that we investigated. Unfortunately, I'm not able to continue my work into the rest of this year, but hopefully continuing progress on this material will make it so that it's potentially competitive with ITO for industrial use and possibly even superior to ITO if we're able to show that it's reproducible and so forth. So I just want to acknowledge a few people who are looking around were able to be here today. My postdoc, Dr. Corson Battaglia, who is very instrumental in just guiding me throughout this entire project. My PI, Professor Ali Javey, who gave me the opportunity to work in his lab, and the rest of the Javey group who were able to provide me just different resources and also insights regarding just the physics behind this project. I'd also like to thank Nathan for all of his feedback and just organization of this program, and Leah for organization-wise of the SURF program, and also the Rose Hills Foundation for funding and just their support of my research experiences. So, yeah, thank you.